I have a job because of biotech and food. I really like the job. It's a really cool job. It's a controversial thing. My dad was a high school history teacher. This stuff allows me to tie a lot of things together that I find interesting. Like language, like whence, whither, and whether. I love it when people say from whence it came, because what does whence mean? From where? So it's this cool thing where the word from is built into it. And whither means, sometimes people say to whither. It's like, no, the whither is built in. And whether, I'm not sure what weather is, but I've already had requests for the other spelling of weather. Yeah. Sorry about that, Win.
It means if.
It means what?
If.
If?
Yes.
Weather means if?
Yeah.
This or that.
Whether or not.
Yeah, whether or not.
That's all it means is if? God, it's so long. All right. Tomatoes. Green, kind of going gold. Really cool because what was the first whole food biotechnology in the U.S. food supply? Tomato. So if you remember back in 1994, that's called the flavor saver tomato, which is a play on words. Because the savor, you're not sure because they spelled it S-A-V-R. And so it was this great play on word. Was it saving the flavor or was it savoring the flavor? Yes. What's that? Or none of the above. Okay. But those are some tomatoes I grew on my parkway this year. And the city of Madison has not yet evicted them. So the reason I wanted to give this talk is, we're 25 years after the first introduction of a whole food, tomato, in the U.S. food supply. Things have been kind of in concrete for a while, not moving a whole lot, and I'm wondering if the game is afoot. And if there is a shift in use or in policy, it's always interesting to ask which crops are coming to market, if any, in which places, with what value added, using which technologies at what cost and for whom. So those are all the things that, those are many of the things that are in play and more. So what are some possible reasons for the possibility of a pivot? I'm not even sure if a pivot's happening, but let's think that it might be. First of all, we're 25 years into this. Closer to 30 if you count chymosin, genetically engineered rennet in the food supply. That means we know a lot. There's a lot of things we don't know, but we also know people are not dying from biotech foods. I used to have my job was supposed to be a food safety job. When I came here in 1991, it was supposed to be on biotechnology and food, and I was in the family living program of the family living program because I was doing a food safety issue. After a few years, it got kind of hard for me to go, how am I doing a food safety issue when nobody gets sick from this stuff? It didn't seem exactly intellectually honest. Not to say it isn't an issue, but it's not the same thing as a food safety issue where people get sick and occasionally die. So that's one of the cool things about this is that there were lots of concerns about safety and use. Would people use them? And sometimes the answer is yes. Many times the answer is no. The boutique crop biotech. We're now at the point where people are doing, because of some of the new technologies, they're able to look at things beyond corn and beans and some of the huge crops and bring some of those to market. So, for example, when we get to the CRISPR part, the first thing on the market that I'm aware of from CRISPR is an apple. The second one is a button mushroom. Those are not huge markets, and yet there are people that are willing to put the time and effort into making these things and going through whatever regulatory hurdles there are. I think another thing that's interesting since 1992 and has a lot to do with agriculture is the whole issue of climate change, and especially their impacts on water and temperatures. The dates are up there just to remind you that this is a long time ago already. So 1992 was yesterday for many of us, but that's when Al Gore's book came out. The Kyoto Protocol was 21 years ago, 22 years ago, I can do math. The movie Inconvenient Truth came out in 2006. That's 13 years ago. So this has been around a long time. This is more than a human generation at 25, 30 years. And how agriculture is going to adapt crops, lots and lots of different crops. One of the things you want to be able to ask is how many different tools are available to the plant breeders. And if they aren't available, why aren't they? Another possibility is the rise of China. First of all, China's not Western. Let's put it positively, China is Eastern. That means they don't have a Germanic legal system or a French legal system or an English legal system. They have different outlooks on how you go about looking at new technologies and regulating them. And therefore, they're a third competing point of view from the North American and the European. They were also, for a while, a very interesting trade partner in agriculture, and then in the last 6 months, now they're a trade war target, which goes to show how these things can be used by different countries in wars of trade. And then this one is the biggest stretch for me, but in thinking about it, 25, 30 years ago, organics were much more of a niche market than what they are today. You had to go to France or England or something if you really wanted to see organics in mainline supermarkets. Well, now you go into supermarkets here, or organics are everywhere. You can get organics at Walmart. And that means it's not quite so a Davy and Goliath situation, that organics have scaled. The prices are more competitive. But because of this increase in scale, there's also the possibility that the folks that are in the organic community may want to, well, their position on biotech in specific and in new technologies in general is something to watch. Because even within the organic community, there's always tensions about what's acceptable and what is not, because there aren't any clear-cut rules. So the twin racetracks. Oh. Question for you. Based solely on shape, are the two tracks identical? They're kind of identical. Great. That was good. I like that. Yeah.
Yes. The rotation is different.
The rotation, yeah, they're screwy. Yes. So what's...
One's left, one's right.
Yeah, what's the deal? This is pretty easy. When I do this with fourth graders, though, they are pretty sure that these are identical. Although there's always a few of them that are going. So if you, what I say to the visitors, if you put a car here and a car here and you're driving both of them, and you go like this, if you're driving this car, which way do you go? Which way you got to turn the steering wheel? Which way you got to turn this way? So scientists test. You can respell how you spell the word scientist and make that kind of like CRISPR, SEIENTEST, because that's a fundamental thing to me that scientists do, is we test our ideas. I tell the kids they can't take this home with them, but they can take this home with them. I ask them, would you please raise your right hand? And they do. And then I ask them, would you please raise your other right hand? The one that is left. And put them together. Are they identical? And God, that's amazing, the arguments. Yeah, they are. Blah, blah, no, they're not. Blah, blah, blah. Are they identical? Are they identical? So this is a metaphor for me and the work that I do in science outreach for one of the functions of education. And that is to help train your brain to learn to discern between two things that are very similar yet distinctly different. And you can carry this wherever you would like, as long as you have two hands. And if you don't have two hands, you have to imagine that. But it's pretty good. Now I'm going to do a metaphor because, again, these are two things that are very similar, distinctly different. Here's the metaphor. And this bears a lot on the CRISPR stuff later on. DNA is a lot like an alphabet. How many letters are there in the English alphabet? Yes, there you go. And I always have to think. And how do we spell different words in English? We put those letters together in different orders to give different words with different meanings. And can we string those letters into words and words into sentences? Sentences into paragraphs, paragraphs into pages, pages into chapters, chapters into books, and books into book series. And if you're J.K. Rowling, can you sell it all for $1 billion? Here comes the trick question. What kind of question? Trick question. How many different letters did J.K. Rowling have to use to write the whole Harry Potter series? 26. So just by having one word different in there, the question goes from how many letters did she have to use to how many different letters did she have to use? So keep in mind, DNA is a lot like an alphabet. The power of an alphabet is you can string the letters together in different orders to give different messages with different meanings, and you can just keep it making it as long as you would like. And can you change the letters? And can slight changes in letters make a big difference in meaning? So for example, bad joke alert, this is a DNA helix. Clearly this is a boy helix because it's a helix. If it was a girl, boy, you guys are fast. Oh, the fourth graders stand there and go. Okay, so there's hope for us. So there's another bad one. When I do this stuff, I have the kids, we extract DNA glot from wheat germ and we have them shake a tube, and while they're shaking the tube for a minute, I sing them the song from 1975, Casey and the Sunshine Band. Shake, 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 shake your booty. What do you get if you take the word booty and switch the B and T around? Shake your tubie. So, again, this is a metaphor. DNA is not an alphabet, but it's a lot like an alphabet. And to be able to hear how these slight changes in letters can make a significant difference in meaning is a bigger deal now than, say, it was 15 years ago when everything was cut and splice. And today we're really looking at what we can do by just making small changes at critical points that make a big difference. What's that?
You missed the toy. You haven't talked about
I haven't talked about the toys. Another thing that's changed since I started here is this. Look, it's Santa Claus DNA. Oh. So this is how people used to sequence DNA. How many letters are there in the DNA alphabet? 4. But the cool thing is, here are 4 lanes. And you had to have 4 lanes because they had only one signal at this time, and that was radioactive phosphorus, P32. And so you had to have a lane for the A, another lane for the T, a third lane for the G, and a fourth lane for the C. And so this was about a day's work in the DNA sequencing facility in 1991, and this is about 600 base pairs. This could be a PhD thesis in the late to mid-80s. Okay. Well, this is nice, but how many letters are there in the human genome? 3 billion. And since there's 2, it's like 6 billion. Okay, you got to do 6 billion sequencing, that kind of thing. So you sequence 3 billion letters, but we got about 6 billion in our diploid genome. That's 6 times 10 to the 9th. 600 is 6 times 10 to the 2. How many of these would I have to do? A lot, thank you. Ladies and gentlemen, at University of Minnesota alum, yes. Okay, well, somebody's got to defend themselves, that's good. 6 times 10 to the 9th divided by 6 times 10 to the 2 is 1 times 10 to the 7th, which is a lot like? 10 million. Okay, 10 million. That's pretty slow. By 1998-99, they had this kind of machine. And this kind of machine, if you loaded it up and ran it really well, could do about 600,000 base pairs a day. That's 6 times 10 to the 5th. 6 times 10 to the 9th divided by 6 times 10 to the 5th is 1 times 10 to the 4th, which is 10,000. Yeah, that's correct. Now, if you had 10 of these machines, instead of this taking you 10,000 days, if you had 10 of them, how much would it take you?
No more than 3 years.
And if you had 100 of these machines, how long would it take you? 100 days. Yeah, it's like a little bit more than 3 months. So in order to do 6 billion, and you got to do it, you got to do it a lot, but you could do the human genome. You start seeing how you get the best technology that you can, and then what do? You get 100 or 200 or 300 of them. And then you end up with the human genome sequence from 2001. Things kept getting better. Whoa. In 2012, we got 2 machines in here that use these. Well, I can't show it to you. This looks just like a microscope slide, because it is, and it's got 8 lanes on it, which is cool. There's a whole bunch of little DNA things on there, a whole bunch being several hundreds of millions. And the 2 machines that we have in there, or used to have in there in January of 2012, could do not 600,000, not 6 million, but 60 billion bases of DNA a day. Okay, so that's 7 years ago. And I asked the guys today, how many can they do in the room? I keep pointing over here because that's where the DNA room is. How many bases can they do a day? And they said, $3 trillion. So that's a bucket. And they can do that because they have machines like this that don't look a whole lot different. They're just like a bigger thing. I have no idea what the technology is here. But it's very cool. The other thing that's pretty interesting is the Snickers bar thing here. So this is the size of a Snickers bar, and I measured it. I ate the measuring device. But trust me, this is about a $500 minion thing from Oxford Diagnostics. This actually doesn't cost $500. This they give you 2 free, and you put the little $500 piece of glass that goes in here, and you can do about 25 gigabases of DNA in about 48 hours for $500. And you can do this in a hospital or in the field or in the Congo. Why would you do it in the Congo, and why did they talk about doing this in the Congo today? Because Ebola, la 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 la. So the technology has rapidly gone up. The costs have gone down. The turnaround time is in 24 to 48 hours. It still is not easy, but we can do a lot of stuff with DNA sequencing and analysis that far exceeds what we could do 25 years ago. And that's what's cool about this. So let's look back a little further. I want to do some, the state is unusually gifted in looking at food issues. I don't know why. Just wait till we get to beer issues. Okay, so do we all know the story from Oleo? Oleo, ole, ole. Oh. Okay, oleo means oil. And for us, it means oleomargarine. Oleo comes from the word for olive. And which oil do we get from the olive tree? Ole. So this is a big deal. Wisconsin's becoming a dairy state in the 1880s, 1890s. Some French folks figure out how to make margarine not from animal fat, but from vegetable oil. Ooh. What does that compete with? Butter. What does Wisconsin do? Bans oleo. What do the federal courts say? Oh, that's an unconstitutional infringement on interstate commerce. You can't ban oleo. What does Wisconsin say? You can't color it because that's a consumer fraud issue. So from the 1890s on, what could you not buy legally in Wisconsin? Yellow margarine. So what did you and your ancestors all do? Hell, why the Kennedys were making rum runs up to Canada. We were going down to Illinois to get ourselves some yellow margarine, because what could you only buy in Wisconsin? Stuff that looked like Crisco, and you had to add the color. Now, in this room, earlier this year, help me out, Kevin from the Wharf gave the history talk. God. Anyway, this is a brain that's not working real well. So Kevin gave this great talk on Steenbach. And I went to school here, and I always thought that Steenbach patented his vitamin D discovery, so that he could control it, and that's true. Only he wanted to, according to what Kevin Walters said, he's got this little thing here where, in Steenbach's words, I wanted to patent the vitamin D discovery so that I could keep it from going into the oleomargarine folks, because if they were able to put vitamin D into oleo, they would have a product superior to butter. Do you guys remember that when he said that? I was in the back and I was floored. I'd never heard that. So think what that means when you have a state where we have something as proud as we are with vitamin D, and the reason we patent it isn't to get royalties, it's to control who can and who cannot use the technology. So then finally in the mid-60s, we were able to have colored margarine. We were the last state that had banned yellow margarine. Here's another case. This is the one on the left here, bovine growth hormone is why I have a job. Let's look at this. Whoa, this is kind of interesting. We're the dairy state. We want cows, and we want cows to give lots of milk and more milk with less feed, and so we do a whole lot of things to do that. And one of the things in the mid-'80s was, wow, what if we could get, using this cool genetic engineering stuff, what if we could get a pretty endless supply of this bovine growth hormone, bovine somatotropin. Bovine growth hormone, it's a protein, it comes from a cow, we can clone the gene, we can purify the protein from the microbe that we put the cloned gene into, we can inject that purified protein hormone into a cow, it increases the milk production. There are some issues for health for cows, but that's true for almost everything that we do to increase milk production. And there are these potential social issues. Wow, what state's familiar with social issues and biotech and food, or at least technology and food? On the other hand, on the other side is, what do we do with cheese? Excuse me, what do we do with milk? We make it into cheese and butter and ice cream and yogurt and pizza. So here's chymosin. Chymosin is that enzyme. The glop is called rennet. Chymosin is the one of the key enzymes in rennet. Chymosin is the enzyme that cleaves some of the proteins in milk so that it'll ends up clotting, making a curd. So chymosin is a protein. It's found in cows, calves, 10-day-old or less. You can clone the gene, you can put it into a bacterium and grow it up, you can get the purified protein. But do you inject it with a needle into the tail head of a cow? No, you pour it into a cheese vat that's full of milk. And this eases cheese production, so it doesn't increase milk production, it makes cheese production easier. There aren't any issues that I know of for cow health, and there are minimal social issues. The only one I can think of is, will that cheese be considered kosher by the rabbis? And that's up to the rabbis to decide. Excuse me. So here's the third one, and this is one I like a lot. There's this good stuff that you can put into milk. It's a vitamin, and it promotes bone health. And it's made from sunshine. Now, there's a bad guy that you put into milk, but it's a steroid. And it's a protohormone. And it was developed using rats. So when I ask people who would be willing to put The one on the right, the one on the left, the vitamin into your kid's milk. Most people go, yeah, that sounds good. Who wants to put a steroidal portal hormone into your milk? Most people say no. And then when you tell them that vitamin D is both, they're like, whoa. So, as somebody who likes words and likes words a lot, this is a really good cautionary tale because both those columns are vitamin D. And that has to do with words and spin. So here are some words that have been used over the last 30 years to describe transgenic biotech and food. Chimeric. What's chimera?
Fusion of two different animals.
Yeah. So like head of a bull and the body of a man was the minotaur in the Daedalus. Transgenic, genetically engineered, gene spliced, modern biotechnology, genetically modified. Frankenfood is from, I think Jeremy Rifkin still gets credit for that. Brilliant fabrication. Genetically manipulated, edited. Whoa, very calm. We do editing all the time, not a problem. Terminator. Golden rice, yes. So people have over the 28, 29 years I've been doing this job, have always been trying to figure out which terms today have the spin that they want to have on it.
Did you try curated genome?
Curated genome. Sounds like bacon. So my favorite example is GMO. So when GMO came out, one of the big questions was, to what are you going to compare these genetically engineered crops? How are you going to test them against what? And so the National Academy of Science, the National Research Council, came up with this term, well, we will call them all genetically modified organisms. What is a GMO? It's an organism that has been genetically modified. It's about as broad a term as you can come up with. And that was 1989. And within a few years, GMO went from being any organism that's genetically modified by any means. It had gone 180 degrees, and now it meant only gene spliced. Whoa. Now, and later, now it means, at least to the European regulators, it means modified by any modern technology. And I have to put modern in there because this is a 25 to 30-year-old term, and we have 10 to 15-year-old technology that doesn't fit real well with only gene spliced. So they've had to stretch this and what modern means. So it's not just gene spliced anymore. And the ones that are the biggest to me is who gets to control natural, and who gets to sling unnatural, and who gets to pin the word artificial on something. This is a really fun essay from 3.5 years ago. It's practically impossible to define GMOs, and it's by Nathaniel Johnson in Grist. So I wanted to let you know about that. So now we're in this day. Since 2012, we have this thing called CRISPR. And CRISPR is an example of being able to change genes a letter at a time. How many of you remember the first time you got on your Wang word processor? It was a miracle. Remember the orange screen? You know, and then you could light up a line and hit it, and that mistake would go away. And I had just finished typing my master's thesis on an IBM Selectric with a magic little thing that if you got to it soon enough, you could hit the magic button, go back and type the mistake that you had made. It would lift it off the paper, and then you could type the actual one on. And when I saw my friends, when I moved up here from the University of Illinois to UW-Madison, and they were writing their theses on this Wang thing, it was like, holy moly. And that's the metaphor. Remember, metaphors are similar, distinct, not the same, but this is pretty cool. Now, we have had examples of being able to do gene editing or turning genes on and off for a while. None of them took off. Don't know why. They were used in labs, but they were too clunky. So you may have heard of RNA interference. zinc fingers and talons are both editing. And to edit kind of means to change a base or two or a few. You can also add. Be very careful, grasshopper. But this whole thing about, wow, we're really not adding anything. We're just changing stuff that was in there already. So this avoids the whole chimera, transgenic, frankenfood spin on this. And I want to, again, I usually bring up the word vitalism. And I think there's a very strong vitalism streak undercurrent in this whole argument about what's natural and what isn't natural, and what we need to worry about, and what's aligned with nature and what's an abomination. But CRISPR is like, whoa, this is cool. Now, is it powerful? You don't have to add DNA. You just need the sequence of the gene that you're interested in, preferably the whole sequence. Is it pretty easy to get the whole sequence now? Does that mean you can go fishing for targets? Can you go fishing for off-target effects? Not perfectly, but much better than we used to be able to do. You probably heard of Cas9. That's the most famous one. There are a whole bunch now. But the key thing is, this is only 2 parts compared to the talons and the zinc finger. And the amazing thing is the Cas9 is the protein that you don't have to engineer. You just have to, you get to build your guide RNA. And how long is your guide RNA? 20 bases, that's hardly nothing. And so it's a very stunning increase in the technology that almost anybody can do it. And that's why the Swiss Army knife analogy is pretty cool. Be careful with all the analogies, careful where you point that thing. But it's easier, faster, more efficient, more precise. It's not perfect. Do not let people tell you anything is perfect. Like a knife, the basic use is to cut something. Well, when you can cut a tape of letters, what have you done to the continuity? Whoa, that's pretty good. And if you cut it and drop a letter or two out and then paste it back together, it may not make sense anymore. In other words, it might wreck the gene. And if you want to turn a gene off, that's not bad. The other thing that's pretty cool about this is, the way genes are set up, there are promoter regions, regulatory regions, usually upstream, what we call upstream of the tapestry of a gene. And if you go into that regulatory thing, you can change up or down how something is turned on or turned off. This is very powerful. Notice we don't have to add big chunks of anything. Hence, again, editing. Now, if you do this right, you can also drop in significant chunks of added DNA. If that's from the organism that you're already working with, for some federal agencies, U.S. Department of Agriculture in specific, that means you're not doing anything that triggers concern for them. For others, EPA or FDA, you might. And for the European Union, it doesn't matter. They've ruled that this is just as genetically modified organism-y as dropping a gene in from another organism. So some of us are familiar with the line item veto and how powerful it is in Wisconsin. And we just saw a very interesting example this past summer, how you can be pretty creative in how you draw lines, and you can go pretty far with a line item veto. And I think that's that kind of, how do we look at what's already in the organism that we can take out or slightly move around, is a different mindset than how we're going to find a gene in a cow and give it to a bacterium and grow it up so we can make the protein. I don't want to disparage the power of genetic engineering at all. I'm just saying this is pretty cool stuff. And then again, this impact on the vitalism mindset. It bypasses it, does not defeat the vitalism mindset. In some ways, it's kind of a little karate, jujitsu thing where it's like, well, you're concerned about this, well, we'll give you a technology that it doesn't really affect it so much. Which concerns me because I don't think vitalism is a very well-supported point of view in the world, but a lot of people, it's important to them. So here's competing metaphors, transgenic, what we had starting from 72, editing, which at least from a CRISPR point of view, from 2012 and maybe another 10 years earlier, but the metaphors are what makes this understandable to me, and I hope you can see the distinction. Why is this so pivotal? Well, the EU Court, High Court, European Court of Justice last July, 13 months ago, ruled it isn't pivotal. That CRISPR crops are going to be regulated just like genetically engineered transgenic crops. But for the U.S. Department of Agriculture, their jurisdiction for a lot of the stuff, regulating a lot of transgenic crops, comes from the idea of the insertion of DNA sequences that come from microbes or viruses that are pests or may become pests. That is a vitalistic mindset in the U.S. statute. So how do you get around that? You don't use any stuff that came from pests or that has any reason to think it might become a pest, like DNA from the crop that you're working on. And one of the key things is that editing doesn't leave behind DNA sequences that originated with possible plant pathogens. Again, that's a pretty vitalistic mindset. But the cool thing is, it allows you to have what's called an unregulated article. USDA does not approve things, they just say it's not regulated. It's an unregulated article. It's a legalistic procedure, that's fine. The FDA does approve things, or say they have no concern, and the EPA approves things. So, I'd like to do some close reading, textual analysis of a letter from 2016. This is a letter of the USDA APHIS people sent to this researcher, Yunong Yang, at Penn State. Oh, wait, that's the Pennsylvania State University. We had better call the Ohio State University because they tried to trademark the last week. Look what he's asking for. I asked you, could you please confirm for me that this transgene-free, CRISPR-edited mushroom is not a regulated article? I sent you a whole bunch of stuff. Now can you let me know, can I move ahead with this? So thanks for sending your letter, asking whether this mushroom is a regulated article. You describe, using this CRISPR-Cas9, and why you wanted to do it. If you take a white mushroom and cut it and leave it out, it does like a banana. What color does it turn? Okay. So the anti-browning trait reduces the formation of brown pigment, improving the appearance and shelf life of the mushroom. Yay. Okay. Whoa. So here's why you wanted to do it and how you did it. Here's our jurisdiction. We're a federal agency. We have to tell you on the basis of what statute or regulation we regulate you. Here's our statute. It gives the USDA authority. They do not use the word power. They use the word authority. Unless, of course, more recent people in other high positions use the word power. Gives the authority to oversee the detection, control, eradication of plant pests to protect agriculture, environment, and the economy. Whoa, notice plant pests. We regulate all these cool things and certain genetically engineered organisms that are or have the potential to be plant pests. On what basis might they be plant pests? Well, because they're using DNA segments from viruses or bacteria that could become a plant pest. That's vitalism, right? And now, here's the act. Here is the federal regulations. This are the nuts and bolts of what you have to follow. And you have to have a reason. So if a genetically engineered organism is a regulated article if it's been genetically engineered using a donor or a recipient or a vector agent, anything that's ever been thought of as a plant pest. Or, if we don't know what it is, we're screwed. Or, if the administrator decides it could be. Okay? But generally they don't. So this is setting us up to say, wow, we don't have any reason to describe this. You did your stuff, but it contains no foreign DNA integrated into the mushroom. The sequences that were used and the plasmid constructs were transiently expressed. That means only for a little while and then they went away. And you can confirm that because you did this thing called polymerase chain reaction and Southern blot analysis, named for Dr. Southern. And wow, you confirmed that there's no genetic material, including these guys, was invested. Whose hands are tied here? The only option that the USDA has is to have the administrator of APHIS say, I don't know about this. And that's not the position of the United States government in the time that I've been doing this. Whether you're a Democrat or Republican, people have been pretty pro-biotech from the point of view of that kind of interpretation. So we've concluded that your mushrooms don't contain any introduced material, genetic material. We have no reason to believe this stuff is a plant pest. Therefore, we don't consider, oh, by the way, there are similar letters, but I don't know where they are. APHIS does not consider this to be regulated according to that. It's not listed here, and we have no reason to think that it's going to increase the weediness of a white button mushroom. I'd never heard of it as a weed, but hey, there you go. So, therefore, we sign this off, and it's April 13th of 2016. And does this mean this person's got to get out of jail free card? Nope. Because what's he still got to get through? EPA and FDA. But this mindset is very different than what, say, some other countries have done. So this is a very good article that I stumbled on while preparing for this. So I want to make sure you can see that. If you want to go look it up yourself, it's called The Bench, and it's in Thigo. Here are the 6 things that this blog post said are in the works with CRISPR. Well, we're going to take this thing that I've never heard of, some Selenium pimp in the elifolium. Well, they're going to try to domesticate basically wild tomato. Not by adding stuff to it, but by primarily knocking stuff out. The white button mushrooms is the one we just went through. Improving yield of rice, resistant citrus greening, which is a bacterial infection spread by a psyllid insect that is wrecking the citrus industry all over the world. I didn't realize that chocolate was at risk because of this Phytophthora fungus, and then removing gluten from wheat. So just 6 examples of how this is being proposed to be used for really important stuff. What are you not seeing here? Wow, there's no herbicide resistance. Oh, there's not much in the way of insect resistance. You want to have insect resistance, but this is very different than, say, the stuff that was done in the late 1980s, early 1990s that became the BT crops and the Roundup Ready crops in corn and soybeans and canola and sugar beet and a few other crops that are so widespread today in the United States and Canada, Argentina, Brazil, and a few other places.
But isn't the point of essentially domesticating Solanum pimpinellifolium because it is more disease resistant than like a Persicum esculent?
I don't know. that might be a good thing to do so that you get less yield drag as you're doing crosses with that. But I don't know. Might be because they want to make that or ground cherry. The ground cherry was another one. They want to make it into something that you can eat. So everybody knows that this beautiful Roma tomato came from Italy. That was where it was first born and growed. Except for, no, it's a New World crop. And, you know, people, because it's in the nightshade family, the classic example is, this thing will kill you. Oh, yes, it will. Okay, the Columbian Exchange. What did the Columbians get for it? Yeah, wow. So in this blog post is this very interesting to me table of gene edited versus genetically modified. And it's like, wow, that's interesting how you can, even in a place that's really pretty pro-biotech, it's like, ooh, DNA is exotic. DNA is native. You can rewrite versus you can transfer. This is very interesting. This one I didn't get. I'm from Wisconsin. We know cows can't fly. Pigs can, but yes. Okay, and then of course one that's underscored is, I wouldn't say the U.S. does not regulate techniques that mimic a natural process. The USDA does not. Okay. So, what are our friends in Europe hoping to be able to do? So one of the cool things, once CRISPR started developing in 2012, 2013, 2014, it's like, whoa, this might be the thing we're waiting for. To get around the European very stringent regulations of genetically modified organisms. So here we got a CRISPR gene cabbage. We growed it, we cooked it, we ate it. It's 2016. Yay, this is good. The Organic Certification Board says gene editing are GM whether you like it or not, at least from their point of view, and they can control their own certification. And then the French government asked the European Court of Justice for a ruling in 2017, and they handed down that ruling in July of 2018, and they said CRISPR is going to be regulated just like all the other GMOs, as they call it. So that really put a stymie on for the plant scientists that were using CRISPR with the hope of being able to use it as a crop improvement tool. So this is basically from that Nature article. So that I did not write this. This is a screenshot from that article. They wanted it to be considered mutagenesis and therefore exempt. The people opposed to GM organisms said, hey, this is still deliberate, as if that increases or decreases the risk. But this is what's weird about this whole field, is what suffices as cause to regulate. Then in January of 2018, Advocate General, which is a person with the court, had this interesting analysis that he did both sides stuff, saying, well, it could be this, it could be that. This is kind of like a court brief. And then 6 months later, the European Court of Justice said, no, CRISPR's going to, because CRISPR is new, it's dangerous. Only mutagenesis techniques that have conventionally been used in a number of applications and have a long safety record are exempt. Except, what are those? And what kind of long safety record are they? Because they've always been exempt, so how good do you know how they're doing? And this is one of the dilemmas with this, is because something is old, it's time tested. And how good is the test of time?
Not necessarily.
Thank you. So, I think I'll stop there because it's 5 to, oh, that clock says it's 5 to 9. Wow, we're ahead of ourselves. I want to point out that when I was working at Agrogenetics, there were 5 groups, and I was in a group trying to get a virus gene, coat protein gene, into crops and have the crops make that coat protein gene all the time, with the idea that somehow that mechanism, that would keep more virulent types of the virus from coming in. That was pretty cool. But what was even cooler to me was this whole idea of, wow, we have this bacterium called Bacillus thuringiensis. There's a whole bunch of different strains. The cool thing is they make proteins. Each strain is a little different based on what kind of insect it kills. But if you're an organic grower, you can grow up BT or have somebody grow up BT for you, turn it into a powder, put it on your cabbage, and when the cabbage looper caterpillar comes along, it eats it, it ingests it, and the BT either kills it or gives it a tummy ache and it stops eating and it dies anyway. Wouldn't it be lovely if we could take that organically approved protein and put it into the cabbage so that it would be made at a low enough level that it would work, but it wouldn't get washed off, it would always be there, you wouldn't have to make the dust and all that stuff. So that was the fervent hope in 1986. Of course, by 1990, when the U.S. organic law was passed, the organic folks had already kind of thought this is not sounding real good to us. In 1997, when the first proposals for the official regulations for organic took them 7 years because of lots of reasons. They included, among other things, genetic engineering, and there's a huge uproar. The final rule did not include genetic engineering. So the reason that genetic engineering is not considered organic is not because the genetic engineering people didn't want it to be that way. It was the organic people said this is antithetical to what we stand for. So I think the point of view of how are we going to look as far as whether we're going to use biotech in the industrialized countries depends a lot on how people look at what is natural, what is unnatural, what's acceptable to them, what is wholesome, holistic, or holy, and what is an abomination. And this is not knowable until you have the conversations. And what happens in the developing world, though, is a little bit different. They still have people going to bed hungry. And we are shifting our food system over to an issue of what they call overnutrition, which we call here in Wisconsin obesity. And that's a little bit different for 5 billion of the 7 billion people on the planet. And I think that's going to play out perhaps in different ways. So why don't I stop there, and I'd be happy to take any questions. Yeah.
You're using CRISPR and you're not allowed to put anything in, but the regulations say that, they can regulate if there's a danger of it becoming a plant pest.
There's a reason to believe.
Right. I don't know too much about plant genomes, but I know that animals often there are leftover viral sequences, viruses that have been incorporated into the genome. Potentially, I don't know if it's ever happened or any type of discussion, eventually you might activate an old virus by editing just what's in the genome.
Yep.
Has that ever been brought up in any of this discussion?
I've seen under transgenics the idea that when you insert, the insertion is random and therefore you can drop something into a place that, yes, it produces the protein that you thought you wanted, but it also inactivates a gene or a space. And sometimes that inactivated gene actually releases the activation of another thing like a virus or a virus that's been latent. So one of the things you have to think about is how is this different, or at least I think they should think about, is this any different of a risk than what we're doing with all kinds of methods of plant genetic improvement? So random mutagenesis, doing crosses, all this stuff. What has been painfully clear to me over the years is we tend to focus on this new stuff and we give the old stuff a get out of jail free card. The National Academy of Science report in December of 2016 addressed that in their summary, which was pretty interesting, where they were saying, wow, these techniques are now getting to the point where the crops are indistinguishable from the kind of plant breeding that classical plant breeders do. How are we going to justify treating them differently? And that whole thing of double standards has long been a bone for me, because it's the analogy that I use. If you're in a river town like Dixon and you decide to build a levee, and part of the area you got a levee that's 10 feet high and another that's 2 feet high, you only have 2 feet of protection. So that double standard approach doesn't make sense to me.
So in the European Union, irradiated crops, changes produced that way are legal.
Based on what I read in there, especially the last part where it's conventionally been used in a number of the applications, long safety record, that would be, let's just hold them near a radiation source, plant them, go out there and select for the ones that we like. We have no idea what happened or how it happened. And this is one of the things that's weird, is the more you know, the more you're responsible for. So the less you know, and I think I sang a song about that in high school, the better off you are, because you just go, I don't know. Again, what's cool about all this stuff is now the price and cost of sequencing your traditionally developed varieties is so low that I think it's coming to the point where you could reasonably ask, have you done your due diligence? Do you know what's different about this traditionally bred cultivar, cultivated variety? If not, why not? After all, we have at least 3 examples of traditional breeding ending up with significant food safety issues, with sorolins in celery and glycoalkaloids in potatoes, and can't think of the third one. I know shattercane was a weed issue. Maybe that's the third one I'm thinking of, where Johnson grass and sorghum ended up making a weed, if I remember that correctly. So to me, that's and I think that's what the National Academy report was getting at in their report 2.5 years ago. It was like, whoa, how long is this going to continue on? Because you cannot tell them apart, because nothing has been added. I shouldn't say nothing's been added. There aren't any sequences that you can say, oh, here's the sequence from entity A that we dropped into this entity B, and that sequence was never in this sequence, and therefore we can tell that that's where it came from.
Potentially evil entity A.
I did not say that. Sandy.
In the science of life cycle assessment, they're moving towards anticipatory life cycle assessment. So I look at that for anticipatory GMOs, and I don't see that much there. I think, is it much more difficult challenge to your science than life cycle assessment? For anticipatory, what's going to happen?
Yeah, I don't know enough about the questions about life cycle assessment, and specifically this type that Sandy's talking about is anticipatory, and I don't know the terms, so it's hard for me to answer, and I don't do plant breeding or this in a nuts and bolts way. So I don't know how to answer. What do you think people might do?
Well, if you just Google anticipatory genetic engineering, you won't see as many papers as you find, and maybe it's my terminology of not finding it. You'll find ethics. Anticipatory life cycle assessment means that they try and think of what's going to happen in the future. For example, is Beyond Meat or Impossible Burger, if they use coconut oil are there enough coconuts in the world to meet the demand?
okay.
What's gonna happen if we do all that? So, that's a difficult, that adds another, dependent variable in your study, and, I haven't seen as much as that for genetic engineering as I have for life cycle
Okay.
assessment.
And I haven't seen any, I didn't look for it, I didn't know it existed, so I can't respond any more than saying I don't know. Other questions?
Is there a rough estimate about how many crops are out there in the world right now? That are,
Is there a rough estimate as to how many crops are out there in the world right now? Yeah, there's an organization that goes by isaaa.org, and in my other talks I usually show here's how many hectares of corn and beans and canola and cotton and sugar beets, and are there any other major crops? And so those are the folks that track that. And it's from 1996 when the first corn and beans came on. It was the fastest adopted technology in agronomy. And then, of course, when you get high enough, there's not a whole lot more that you're going to be able to get. And then the question is, like with Roundup Ready Palmer Amaranth and dicamba and all that stuff, what's keeping people using this if they start getting Roundup resistant weeds, or if you switch to dicamba, then you have drift issues. And so that's, again, one of the things that's interesting about CRISPR is that the patent situation so far is there's an easier road to smaller companies to work with smaller crops, and that the barriers to market seem to be smaller than with the transgenics, where you had to add something. And in the case of Roundup Ready, you wanted to have not only sell the seeds, but sell the herbicide. And that's, again, when I'm showing you that list, that's not on the list of things that are being cooked up. That doesn't mean that Bayer, who bought Monsanto, isn't using all this stuff in spades. It's just that that source doesn't know about it and so didn't mention it. I don't know what people are doing that they're not talking about. Other questions? If not, thank you very much. Appreciate it.